All right, today I'm going to show you all how to verify the behavior of an op-amp circuit using LT-Spice. So I'm going to create a new schematic. I'm doing that by clicking the new schematic icon in the top left, and it brings up a blank grid. I'm going to make my grid a little smaller by zooming out. I do that by pressing Control and then scrolling up on my mouse's scroll wheel. And this is just going to allow me to fit more components into an area. Now the first thing that I'm going to do is I'm going to establish all of the different voltage sources that I'm going to need for my circuit. I'm going to need a positive power supply voltage, a negative power supply voltage, a reference voltage, and an input voltage. So let's start with my power supply voltages. I'm going to click on the component button, and I'm going to type in the word voltage. And that allows me to place voltage sources into my schematic. I'm going to put 2 down, and they're going to almost be on top of each other. I'm going to wire the positive polarity terminal of voltage source V2 to the negative polarity terminal of voltage source V1. And then at that node, I'm also going to make a little stub, which is going to be my reference terminal. So I'm going to set that to ground. I'm now going to use the label net command to label the positive polarity terminal of V1, which is going to be VCC plus, representing my positive voltage supply. And I'm going to use the label net command to label the negative polarity terminal of voltage source V2, which will be VCC minus, my negative power supply. If I right click on component V1, I can then set the DC value of this source. We are expecting a positive 5 volt DC supply, so I'll put in 5 and hit enter. And for my negative power supply voltage, we are expecting negative 5, so I'm going to hit positive 5 and enter. And the reason why I use positive 5 is because the positive polarity terminal is at 0, and there's a 5 volt drop over this source, so VCC minus must then be 0 minus 5 is negative 5 volts, and we will verify that shortly. Let's next do my reference voltage. So I'm going to put another voltage source into my schematic. I'm going to give myself a little stub with which to ground, and then I'm going to use the label net command and type in VREF to let me know that this is my reference voltage. For our example, it should be 2 volts. Finally, I have my input voltage. So let's go ahead and put a voltage source in. Go ahead and put our stub and ground it. And then label it as VN. Now, for homework 2, problem 3, our input voltage is expected to range from negative 5 volts to positive 5 volts. So I'm going to accomplish that by using a sinusoidal voltage source. So I right click on this voltage source V4, go to the advanced button, and choose sine. Now I want it to range from positive 5 to negative 5, which means it has an amplitude of 5 volts. And I'm going to choose my frequency to be 1 hertz, or 1 cycle per second. This is purely to make the math easy. You could do 60 hertz here or 10 kilohertz. It really doesn't matter. I'm just choosing to do 1 hertz. And all of the other parameters I can leave blank. So the next thing I want to do is make sure that all of my voltage sources are behaving as I would expect them to do. And I'm going to accomplish this using a transient analysis. And because my sinusoidal source is running at 1 cycle per second, I'm going to stop this simulation at 3 seconds so that I'll see exactly 3 cycles. That should be plenty of time for me to see anything weird that happens. I can now click the running man icon to run my simulation. And it pulls up a blank plot window because I haven't told it what to plot yet. I'm going to go ahead and make my schematic a little bit larger so that I can see more specifically where my voltage probes are. So when I mouse over a node point, I get a voltage probe, and when I mouse over a component, I get a current probe. I'm looking for voltages, so I want to be over a node point. So let's check the voltage at the node VCC+. If I left click there with my voltage probe active, it generates a plot of the voltage at node VCC+ with respect to time. This is a DC source that is supposed to be supplying 5 volts, and I can see that it has a value of 5 volts for all values of time that are in my simulation, so that seems to be behaving properly. I can now check VCC minus, and I see that it's at negative 5 volts for all values of time, which is exactly what I wanted. I can check V reference, which is exactly 2 volts for all values of time, again what I wanted. And finally, I can look at my input voltage, and I see that I get a sinusoid, which is oscillating between 5 volts and negative 5 volts. So that seems great. So all my voltage sources are doing exactly what I want them to do, so I can go ahead and shut down this plot window for now and make my schematic window larger again. I'm going to zoom out, and I'm going to move everything to the left just to give myself a little room, and now it's time to work on the actual op-amp circuit. The op-amp that I'm going to use is called Universal Op-Amp 2. The reason that I choose to use this particular component is because it has lots of editable parameters. If I right-click on this op-amp, I can see here in the lines that say value, spice line, and spice line 2 that I could change the open loop gain labeled AVOL. I could change the slew rate labeled slew. I could change the input resistance labeled RN. I could limit the amount of current that can be output by the op-amp by editing the iLimit parameter. There's lots of different options for me to edit here. I don't need to mess with any of these for right now though. One thing that I do want to ensure is that the level of the spice model is set to level 2. The reason why I want it to be at level 2 is because level 1 treats the op-amp as an ideal op-amp, meaning that it doesn't care what its supply voltages are. It is going to amplify the signal how it's supposed to and never take into consideration saturation distortion. Because the comparator works due to saturation distortion, I need to have it at least on level 2 in order to capture what's supposed to be going on here. So I'm going to click OK, and now I'm going to draw a few stubs, one at my output terminal, and then one for each of my input terminals. And I'm going to use the label net command to then apply voltages to my op-amp. So I can start with VCC plus, and I put this VCC plus label on the positive power supply terminal. And what's going to happen is anywhere I have VCC plus, this text written, it's going to apply this 5 volt source to that. So this lets me apply my voltages without having lots of components actually connected to my op-amp, which are going to muddy things up. I can do a similar operation for VCC minus, apply it to my negative power supply terminal. Now let's do V reference. And let's look at a non-inverting comparator, which means my reference should be on the inverting terminal. I'm going to apply the voltage Vin to my non-inverting terminal, and I'm going to label the output as Vout. Now I'm ready to run my simulation. So I click my Running Man icon again and make my schematic fit its window, and I'm going to plot Vin as a function, or excuse me, Vin and Vout as a function of time. That's what the transient analysis lets me do, plot things as a function of time. So I'm going to change my axes, or the limits on my y-axis, to positive 6 volts, ranging down to negative 6 volts. To be clear, I did that by mousing over the y-axis and then right-clicking. And I can see that whenever my input voltage is greater than 2 volts, which is this part of the green curve here, my output is saturating to positive 5 volts. And whenever my input voltage is less than 2 volts, which is this part of the green curve, my output saturates to negative 5 volts. So this is the exact behavior I should expect for a non-inverting comparator with a reference voltage of 2 volts. That being said, this is not the plot that you were actually asked to generate. It does verify the behavior of the op-amp circuit, but you were specifically asked to plot V in versus V out. How we're going to do that is we're going to delete V in, the trace from our graph, and then we're going to move our mouse cursor to the horizontal axis until we get the ruler, and we're going to right click. Notice here at the top that we can specify the quantity plotted on the x-axis. Right now it's time, but I could change that. So what I want to change it to is my input voltage, so I do V open parentheses V in. Press OK, and now I can see that my x-axis is my input voltage and my y-axis is V out. I'm going to go ahead and change the limits on my y-axis again just to make things a little clearer. Positive 6 volts and negative 6 volts. And I can see now definitively that for values of V in that are less than 2 volts, I have an output voltage of negative 5 volts. And for input voltages that are greater than 2 volts, I have an output voltage of positive positive 5 volts. So this behavior should match identically your hand plot of V in versus V out for the non-inverting comparator. It should be pretty trivial at this point to detail how a inverting comparator will work, so I'll leave that to you all. Thanks.